Here we introduce something a little more general. It's called a power series centered at A. And this is a power series of the previous form, except the x is replaced by x minus a. This is an infinite sum of the form, the sum from 0 to infinity of Cn times x minus a to the n. The c's here are constant coefficients, and the terms of the series are a constant coefficient times x minus a to the power of n. And the reason for this is sometimes we want to shift our focus to concentrate on how a function behaves around a point x equals a. And we would like to get a power series expansion for the function centered at that point. Notice that when x is actually equal to a, this thing is going to converge. So when I plug in x equals a here, where a is some constant, I get the sum of C0 plus C1 times a minus a plus C2 times a minus a. So any term with a power bigger than or equal to 1 here becomes 0, and the infinite sum is just C0 plus 0 plus 0 plus 0, which is C0. So this always converges when x equals a. And notice also that if a were equal to 0 here, then this would just be a power series similar to the ones I looked at before. It would be the sum of Cn x to the n, which is similar to the power series in our original definition and in the previous examples. So for example, the sum of x to the n over 2 to the n, this is a power series centered around a equals 0. This new definition encompasses the previous definition that we had, and it's a more general definition of a power series. Let's look at an example. The power series given below is centered at 1. The formula is given by the sum from 0 to infinity of x minus 1 to the n over 3 to the n times n plus 1 cubed. If I plug in x equals 2, I get that the value of this power series is the sum from 0 to infinity of 1 to the n over 3 to the n times n plus 1 cubed, or the sum from 0 to infinity of 1 over 3 to the n times n plus 1 cubed. And you could see by comparison with the series, the sum of 1 over 3 to the n, that this converges. Now, it's not as easy to say exactly what that sum is, but we do know that x equals 2 is in the domain of the function defined by this power series. Actually, it's pretty easy to find the domain of the function defined by this power series. For any given value of x, we can tell whether the series converges or diverges using the ratio test, except maybe at 2 points, which we'll get to at the end. So for any value of x, and let's not specify what that x is, let's apply the ratio test and see what we can conclude. The series we're looking at is the sum from 0 to infinity of x minus 1 to the n over 3 to the n times n plus 1 cubed. Ignoring what x might be for the moment, let's assume that we've fixed it, but we're not specifying what its value is. Then applying the ratio test, we calculate the limit as n goes to infinity of the absolute value of the n plus 1th term over the nth term. So it's the limit as n goes to infinity of the absolute value of x minus 1 to the n plus 1 over 3 to the n plus 1 times n plus 2 cubed, divided by the absolute value of the nth term, which is the absolute value of x minus 1 to the n over 3 to the n times n plus 1 cubed. Now, it's crucial here to keep the absolute values, especially around the x minus 1 part, because we don't know what x is. It might be greater than 1 or less than 1, and we'll see that it's really important to not discard the absolute values at this point in our calculation. So this is the limit as n goes to infinity of the absolute value of x minus 1 to the n plus 1 over the absolute value of x minus 1 to the n times 3 to the n over 3 to the n plus 1 times n plus 1 cubed over n plus 2 cubed. So after cancelling x minus 1 to the n and 3 to the n, we get that this is the limit as n goes to infinity of the absolute value of x minus 1 over 3 times n plus 1 over n plus 2 cubed. And notice that the absolute value of x minus 1 over 3 has no n in its expression, and it doesn't depend on n in any way. As far as n is concerned, that's a constant. It's not changing. And x is some number, but we haven't specified what that number is. So I can pull that out from under the limit, and my limit is the absolute value of x minus 1 over 3 times the limit as n goes to infinity of n plus 1 over n plus 2 cubed. That limit of the rational function of n is equal to 1, so my entire limit from the ratio test is the absolute value of x minus 1 over 3. And as we might have expected, it depends on what the actual value of x is. Remember that the ratio test says that my series converges if this limit, the absolute value of x minus 1 over 3, is less than 1, and it diverges if the absolute value of x minus 1 over 3 is greater than 1, and I have no conclusion if the absolute value of x minus 1 over 3 equals 1. So from that we can conclude that the series converges if the absolute value of x minus 1 is less than 3, and that's the same as saying that minus 3 is less than x minus 1, which is less than 3, and then adding 1 to both sides of both of these inequalities, I get that that's the same as saying that minus 2 is less than x, which is less than 4. So this gives me a set of x values where the series converges, and I can also say it diverges if the absolute value of x minus 1 over 3 is bigger than 1, and that's the same as saying that the absolute value of x minus 1 is bigger than 3, and that is either x minus 1 is bigger than 3 or x minus 1 is less than minus 3. And that's the same as saying that x is less than minus 2 or x is bigger than 4. So there are only two values left where we don't know what this series does. That is when x equals minus 2 or x equals 4. And in both of these cases, the ratio test is inconclusive. We have to use our previous tests for convergence and divergence to try to figure out what's going on here. So far we know that this series converges for x values between minus 2 and 4, not including minus 2 and 4. It diverges for x values less than minus 2 or bigger than 4, and we have no idea yet what happens when x is minus 2 or x is 4. And we look at these last two cases individually. When x is minus 2, I just plug in x equals minus 2, and I get the series, the sum of minus 3 to the n over 3 to the n times n plus 1 cubed, and I have to figure out whether that series converges or diverges. Well, cancelling the 3 to the n, I get that it's an alternating series. It's the sum of minus 1 to the n over n plus 1 cubed. So I could use the alternating series test to show that this converges, or I could also show that it actually converges absolutely by comparison with the p-series 1 over n cubed using the limit comparison test. Either way, I see that my power series converges when x equals minus 2. And when x equals 4, I plug in x equals 4 into the definition of the power series, and I get the sum of 1 over n plus 1 cubed. This converges by the limit comparison test, comparing with the p-series, the sum of 1 over n cubed. So I get that my power series converges at both ends of this interval from minus 2 to 4. So the full interval of convergence of the power series is every x value between minus 2 and 4, including the endpoints.